So today we're going to do the third lesson of Module 1 in electrical distribution. And what we're going to be looking at here is the three other power stations that we didn't look at already, and that is your hydroelectric, your diesel, as well as your nuclear power station. So we've already looked at your steam power stations. Now we're going to concentrate on the three that is on the slide. So the first one is our hydroelectric power. And in this scenario that you have, we have what we call a pump storage system in our hydro. And your first top picture is showing when we are generating electricity. So you've got water that comes from the reservoir up on top with the blue arrows going down what looks like a mountain into your generator so that they can be able to produce electricity. Then at the bottom picture, you have what we call now the pumping stage, which means now when you are no longer generating and you've got excess supply on your system, you can now take water back from where the river is and pump it back into our reservoir. So we call this entire unit that we never lose any of the water. We basically just move it from up to down and then we move it back up again so that we can be able to generate. And your generating station will utilize potential energy of water when they're at the high level for generation of your electricity. And these hydroelectric power stations are generally located in hilly areas where your dams can be built conveniently and large water reservoirs can be obtained. The waterhead is created by constructing a dam across a river or a lake, and from that dam, water is led to your turbine through those pipes, and then that water turbine captures the energy in the falling water and changes the hydraulic energy to mechanical energy of your shift turbine. And then your turbine will drive your alternator, converting that mechanical energy into electrical. Then again, looking at your location for these hydroelectric power stations, we want them to be at sites where the availability of water is not an issue, since the primary requirement of these is the availability of huge quantities of water. So you'd want to build these in places like where there is a river or a canal so that you can have that adequate water available for you. Then we talk about the storage of water. There are wide variations in water supply from a river or canal during the year. So what we need to make it necessary for us to be able to store water when there are greater water times during the year. And this we do by constructing a dam in order to ensure that the generation of your power can happen throughout your year. So that it's not a seasonal thing only when there is great rainfall. Then we talk about the cost and the type of land that you're going to utilize, and we want your land for construction of the plant to be at a reasonable price. And further, the bearing capacity of your ground should be adequate to withstand the weight of the heavy equipment that we need to install so that we can be able to do the pumping as well as the generation. Then for transportation, we want the site to have accessibility either by rail or road so that your necessary equipment and machinery can easily be transported. So from these, it's quite clear that your mentioned factors that are ideal for your choice of site is to be near a river and is to be on a hilly areas where dams can be conveniently built and large reservoirs can be then obtained. So the first example that we're going to be looking at on our calculations of your consumption and capacities of these is in example 2.6 in our textbooks. And over here they say we've got a hydroelectric generating station that is supplied from a reservoir, which has a capacity of 5 million cubic meters at a head of 200 meters. So they want us to find the total energy available in kilowatt hours if your overall efficiency is sitting at 75%. So for us to be able to do this, we start off by working out what the weight of the water available is going to be. And for this, we say it's the volume of water multiplied by the density. So for density, we utilize 1,000. And then we know that the volume of water has been given as that 5 million cubic meters. And we get that in kgs as an answer. Then we move from there and we say the electrical energy that is available is going to be equal to your weight. We multiply that by your speed in which the water goes down, in which case this is your gravitational force, multiplied by the meters that your head is above ground level, and then we multiply as the last one by our efficiency. So therefore, it's going to be that 5 times 10 to the 9 that we got above for the weight. Then our age is going to be equal to the 9.81, which is your gravitational pull. And then you multiply by the 200 of you. That is how further down it goes. And then we multiply by our 0.75 for efficiency. We take all of that and then we divide it by 3,600, and that really is going to stand for your hours. So it's your hour times your minutes into seconds, and then there is 1,000 there so that we can get this to a nice value of kilowatt hours, and then we get that answer of 2,043,750 kilowatt hours. And here they were just showing that 1,000 that we used initially, that a mass of 1 meter cube of water is equal to 1,000 kg. Then we go to the next example, 2.7, and in here they say it has been estimated that a minimum runoff is approximately 94 meter cubes per second will be available at a hydraulic project with a head of 39 meters, and they want us to determine the firm capacity as well as the yearly gross output, and we must assume an 80% efficiency of your plant. So we start again by the weight of your water that is available, which is going to be the 94 cubic meters per second, multiplied by the 1,000. Remember, we said 1 mass of water is equal to 1,000 kilograms, so we get that to be kilograms per second. Then we know that the water head was given to us as 39. So our W times H is what we got, times your gravitational force times the 39, which is going to give us that 35.963 times 10 to the 3 kilowatts. Then from that point, only now we're going to go and answer the question of your firm capacity. So your firm capacity is simply your plant efficiency, which was 80% given to us, multiplied by our gross plant capacity. And our gross plant capacity is the same as that work done per second that we have just worked out now. So we end up with the 0.8 times that 35.963, and we get the 28.770 kilowatts. Then your yearly gross output is mainly your firm capacity, which you just did in number 1, multiplied by the hours in a year. So we know that our hours in a year is equal to 7860, and you can do the calculation. And therefore, we take that 28770, we multiply it by the hours in a year, and then we are able to get our kilowatt hour that we would utilize. Then we go to the next example, and this one is sitting at 2.11 in your textbooks. And this is quite an involved one with a lot of scenarios in it. And I think in the textbook, you also have a similar one to it, being at 2.10. So here they say we've got a factory located near a waterfall where the usable head of power is at 25 meters. Your factory requires continuous power of 400 kilowatts throughout the year, and the river flow in a year is equivalent to this. So for 4 months in a year, you get 10 cubic meters per second. For 2 months, you get 6, and then for another 6 months, you get only 1.5 cubic meters per second happening. So they say if the site is developed as a run-of-river type of plant without storage, determine the standby capacity that would need to be provided. And you must assume that your overall efficiency of this plant is sitting at 80%. Then in your second question would be if a reservoir is arranged upstream now. That means a reservoir, you've got some storage space. Will any standby unit be necessary, and what will be the excess power. So the first part of us doing the solution, we first look at the fact that this type of plant is where your whole water stream is allowed to pass through the turbine. Okay, so if you have that 10 cubic going, or you have the 6, or you have the 1.5, all of it is just allowed to be able to go through. And your plant utilizes the water as and when it's available. So when there's a 10, it utilizes the whole 10. When there is the 6, the whole 6. When there's a 1.5, the whole 1.5. And consequently, more power therefore can be generated during your 10 cubic meters per second season and your 6 cubic meters per season compared to your 1.5. So when we discharge the 10 cubic meter per second, we will have the weight of water available being the 10 multiplied by 1,000, which is 10,000 kilograms per second. Then when we talk about the water head, it will be the 25 meters, but we must remember we only have an 80% efficiency. So our age will actually be equal to that gravitational pull of 9.81 multiplied by the 25 meters multiplied by the 0.8 of efficiency. And then if we take that and we multiply it by W that we got on top for your weight, we'll have our work done per second, which is the 1,962. Then when we are using the 6 cubic meters per second, you will now have your work done being your 6 times your 1,000, which will be your weight, and then your age being the 9.81 times the 25 times the 0.8, and that will give us 1,172 kilowatts. Then your last one will be when for the 1.5 cubic meters per second, and the work done there will be the 1.5 times 1,000, then multiplied by our age, which is the 9.8 times 25 times 0.8, and we get 294 kilowatts. Now, what we want to see here is that when we do the 10 cubic meters per second and the 6 cubic meters per second, you can see that we will get more than 400 kilowatts, which is what we require for us to run our factory. However, when we are on the 1.5 cubic meters per second months, okay, which is actually 6 months, half a year, your power developed falls short, and consequently, you will need to have standby units for the entire 6 months of your 1.5 cubic meters per second. And that standby unit, really, for you to calculate it, you're going to take that 400, which is what you require in your factory, minus the 294.3, which is what we're able to achieve. And that means that we need a capacity of standby of 105.7 for a period of 6 months to run this plant. Then the second part of the question was saying that with the reservoir, when the reservoir is arranged upstream, we can store water, and that will permit our regulated supply of water to the turbine. And for us to be able to know what the average discharge is, we take the 10 cubic meters per second that we get in the 4 months, we add it to the 6 cubic meters that we get in 2 months, and then the 1.5 that we get in 6 months. You divide all of that by the 12 months so that it can show that it is per year, and we're trying to get the average per month. And that average per month is basically going to be 5.08 cubic meters per second. Once you have that average, you can then do the multiplication for your power. You take that, you multiply it by your 1,000, which is your 1 meter cubic into 1 kilogram. Then you multiply it by your age, which is the 9.81 times 25 times 0.8. And you will now have a power developed that we're saying is an average for the year of 996.7. So since your power developed is more than required by the factory, you do not require a standby unit in this case. You instead have an excessive power of about 596.7. Then here is the tutorial problems that are found in the textbook under the hydroelectric, and I'm not going to do them now, but we can do some of these questions as part of our virtual face-to-face learning. Then we move on to your diesel power stations. And your diesel power engines are utilized as the prime movers for your generation of electrical energy. And the diesel basically burns inside the engine, And the working fluids, what we name is the working fluids, is what is coming out then of that engine from the combustion will produce our mechanical energy. They are what is going to go and drive the turbine. So your diesel engine drives the alternator, which is a turbine, converting your mechanical to electrical energy. And this is a typical picture of how a diesel schematic arrangement looks like, where you have got your fuel tank and you even have a day tank that you can be able to utilize. And therefore, you will come from that fuel and you inject your pump to go into your system, and then the work will start from there, following the arrows up until we get back to the generator. Then here we've got some calculations that are being done, and the first one is on 2.14. And this one is saying we have a diesel power station that has a fuel consumption of 0.28 kgs per kilowatt hour, and our calorific value of fuel is 10,000 kilocalories per kg. They want you to determine your overall efficiency as well as the efficiency of the engine if your alternator is only at 95%. So we start by heat produced by the 0.8 kgs of oil is going to be the 10,000, which is a kilocalories per kg, multiplied by that 0.28, which will give us 2,800 kilocalories. Then your heat equivalent of 1 kilowatt hour is still 860 kilocalories. So therefore your overall efficiency, being your electrical output in heat divided by your heat of combustion, will simply be the 860 divided by the 2,800 that we got, giving us 30.7%. Then your engine efficiency is going to be your overall efficiency divided by your alternator, because remember those two multiplied together would have given you your overall efficiency. So it's going to be the 0.307 divided by the 0.95, and that will give us 32.3%. Then you have the second example here, where is it 2.15 in our textbook, where we have a diesel power station with the following data: a fuel consumption per day, a units generated per day, calorific value, efficiency of the alternator, and the engine mechanical efficiency. Then they say we must estimate the specific fuel consumption, overall efficiency, as well as our thermal efficiency of our. So here we start with our solution, and basically for the specific fuel consumption will be the 1,000 divided by the 4,000, and that will give us the 0.25. The heat produced by your fuel per day will be a fuel consumption per day times the CV value, and that is the 1,000 times the 10,000 calories per kg. Why are we not multiplying that by our 24? Because already is given that it is happening in per day, all the units in the question. Then we go on and work out our electrical output in heat for the day as well. Is just going to be the 4,000 multiplied by the 860. Why again are we not multiplying by the 24 for the number of hours in a day? Because the question gives it to us as 4,000 kilowatt hour per day is produced at that 4,000. So therefore we get an answer of 344 times 10 to the 4 kilocalories, and our overall efficiency will simply be what we just got now as your electrical output in heat, and we divide it by our heat produced, which was the 10 to the 7, and that will give us 34.4%. Then once we've got that, we can be able to do our engine efficiency, which is going to be your overall efficiency divided by your efficiency of your alternator, and that will then give us 35.83%. So your thermal efficiency will simply then be equal to your engine efficiency divided by your mechanical efficiency of your engine, and that would be able to give us 37.71%. We're now running a bit out of time on the lesson, but anyway, we're going to do example 2.16, where we have a diesel engine that has got a power of 700 kilowatts and two other engines of 500 kilowatts each. And you have got your fuel consumption at 0.28 kg per kilowatt hour, and your CV of your fuel being 10,200 kilocalories per kg. They want you to estimate the fuel oil required for a month of 30 days and your overall efficiency. Plant capacity factor is equal to 40%. Now, here's a question I was asked last year, I remember in classes. What happened when they just ask you to say required for the month and they don't give you the number of days for that month? Knowing that we've got a February at 28 days, some months at 30 days, and some months 31 days. Well, if they don't give it to you, then you should assume a 30-day period, unless they've given you exactly the number of days. So your solution here, you go to your maximum energy that can be produced in a month is going to be your plant capacity times your hours in a month. So your plant capacity is that 700 plus your two 500s, which equals to 1,700 kilowatts. Then your number of hours in a month is really going to be your 30 days that you have multiplied by the 24 hours that you have in a day, and that gives you the 720 hours. And that combination will give you this 1.124 times 10 to the 6 kilowatt hour. Therefore, your actual energy produced in a month is going to be your plant capacity times your hours in a month, which is the 0.4 times the 1,700 times your 720. And that is going to give us your 489,600 kilowatt hour. For your fuel oil consumption in a year, in a month, it's going to be your actual energy in month times your fuel consumption, which is the 89600 times your 0.28. And that will give us the 137,088 kg. So for your second part of your question, your output is really this 89,600 that we got at the top of this slide, multiplied by your 860 kilocalories, and that will give us 421.06 times 10 to the 6 kilocalories. Then your input is equal to your fuel oil consumption in a month times your CV value, which is that 137,088 multiplied by the 10,200. And then for our overall efficiency, it will simply be your output over your input. And your output being the 89600 times the 860, and your input having been your 137,088 times your 10,200, which will give us 30%. We have now unfortunately reached our end timing for the recording of these lessons. So for our nuclear power station, we're going to do it as part of lesson 3B. And we'll explain about the nuclear plants, and then we will have completed your module 1 entirely. Thank you.